Hello, my name is Captain Neil Moores, and today we are talking about how graph theory principles are used to improve computational linear algebra when solving sparse matrix systems. Specifically, we're going to look at minimal degree algorithms to reduce fill in our solution sets. The problem we're looking at is as we collect more data and improve our computational capabilities, we have reasons to solve larger and larger systems of linear equations. Many of these are sparse systems, meaning that there are many zeros in the system that we can exploit. This is important because matrices are becoming too large to store in traditional formats, as there's not enough storage space on any servers that can store some of the large matrices we're getting these days. For example, a relatively small 1 million by 1 million matrix would take over 7 terabytes to store in traditional formats of double precision numbers. So we use the sparse matrix format to start ignoring these zeros and have developed algorithms to reduce the filling of the zeros as we solve these systems. Reordering the elements of these matrices provides benefits when solving these sparse systems. Solving techniques can fill in the matrices for our solution, so it's important to keep them sparse while solving the system. Finding the best solution is considered NP hard, but we do have techniques that have been proven to improve the reduced fill orderings. We use principles from graph theory to take advantage of the sparseness and the relationship between the elements. So this is the most basic representation of what we are trying to get done. We're looking at a permutation of A is equal to a lower times an upper, where P is the permutation of A that reduces the fill of L and U. Note that if A is a positive definite matrix, we can use a Cholesky, which requires we only store one matrix and is therefore a preferred method. Now, if you look at the two matrices, they have the same number of elements in the original matrix, but when we do our LU breakdown, there are 24 non-zero entries in the original ordering, whereas the reordered solving has 21 non-zero entries, meaning we've reduced the fill by over 12%. It may seem small on this matrix, but it can have large effects down the line in large matrix systems in speed and storage capability. We create a graphical representation of our matrix by looking at the non-zero elements of the matrix. We have a vertex representing each row column in our graph. For each element ij that is non-zero in our matrix, we put an edge connecting the I and j nodes of our graph. We only need to do this once per combination of ij, so no double edges if the matrix is symmetric, which makes this process even easier. Now that we have our graph, we can now use the minimum degree algorithm to generate our permutation. So we look at the graph on the far left and see that nodes 2 and 5 are of minimum degree. We select one, in this case 2, for removal, and use that as the first element of our permutation. We then look at the new graph generated by removing 2, and we see that 3 and 5 are the elements of minimum degree in this graph. We choose 1, in this case 3, to be the next element of the permutation, and then we go on to our next iteration, where we look for the lowest degree, and continue this until we have gone through all the vertices. As we continue our algorithm, we remove edges and vertices from the lowest degreed node until there are no remaining edges. In the end, we add the final nodes that have no degree after our edge removals to get our final permutation. As you may have noticed, this does not generate a unique output. There were multiple times when we had more than one node of lowest degree. There are benefits to different choices for which one to remove, but that is outside the scope of this introduction. Let's look at an example from an actual matrix. In this case, we're using the EX9 matrix from the Texas A&M Sweet Sparse collection, which is a publicly available collection of large sparse matrices from various fields. This particular large matrix was generated in the 1990s and is related to fluid flow problems. We see value added immediately from going from the dense storage format to the sparse storage format. Only storing the non-zero elements saves significant amounts of space. Since this is a positive definite matrix, we are using the Cholesky to solve this primarily because it means our solve only has to store a single matrix. What we see in solving the original column ordering gives us an answer approximately 1.6 times the size of the original matrix, whereas the reordered solving is only approximately 1.1 times the original matrix. On a small matrix like this, it doesn't make a significant amount of difference, but as we get to larger and larger matrices, those percentages start to add up a lot. The key from this discussion is that graph theory gives us the tools to discuss and solve problems that were outpacing our abilities in terms of hardware in many problem fields. There are many other ways to apply these principles, each using different properties of sparse matrices to attempt fill minimizing orderings. None are guaranteed to get the ideal solution. As we mentioned previously, it is an NP-hard problem, but we can demonstrate that they improve on the original matrix ordering in terms of keeping the solved problem more sparse. This concludes the introduction to how graph theory helps keep matrices sparse using degrees and neighbors. I hope it's given a glimpse into why graph theory is useful in framing problems from other fields, and how it can be used to improve computational efficiency.